So yeah, so the name is the Triton Machine. That's so basically for the so maybe a new idea for the the Triton CPU, the next version. Okay, so let me just okay, so what is that? So basically the Triton has been only for the GPU, right? But the I did a scratch, I quick
开这个
experimentation.
会还是那个？
Oh yeah, but the it looks like the core parts of the Triton, I mean the GPU, can be reusable for the CPU or a bit more stretched the two non-GPUs. So why? The reason is that the layout system and the TTGIR were actually pretty general to capture the CPU behavior. So I might propose like a Triton machine idea, so which is directly based on the Triton core for the non-GPUs. So it's not based on like a lineage or the other upstream dialects. So yeah, that's basically what I want to discuss today. Yeah. Okay. So yeah, the motivation was that yeah. So I was working for the Triton CPU, and also when it comes to Triton shared, so they do have the different approaches to the Triton, right? So the Triton CPU are using the vector dialect, the shared using the lineage the dialect. So only TTIR is shared with the original Triton. And one of the downsides for me was that the knowledge and experience were not shareable between those two domains. So I was already thinking whether we can use more of a Triton. So this was also motivated by the Tritons, the refactoring for the NVIDIA and the AMD, right? There used to be only the NVIDIA, but the AMD comes in, and the NVIDIA did some good, pretty decent the refactoring and the generalization for those capture the two different GPUs. But what about the other non-GPUs? Can you do it? So that was one of the also my motivation. And this might be controversial, but so I do believe in the long run, having an in-house core framework would be better. For example, the Triton, we use our own dialect, our own implementation, not rely on the upstream dialect. So the vector dialect was a really good the shortcut for the Triton CPU, the first version, which works very well. But the now I am feeling a bit more restrictive. It is okay, it's working, but we don't have any tensor types, for example, after Triton CPU IR. So there is some restrictions are there. I am also hearing similar anecdotes for the lineage dialect when it comes to Triton shared. So yeah, that was the kind of my motivation. Very quick overview for the layout system in the Triton. So everybody knows that. So the Triton operations are written based on the layout. So layouts, I think this is a really key part of our Triton system. And that these layouts are attached during the TTGIR construction time. And that the layout is distributed layout. So it captures 4 levels of the compute hierarchy in the GPU or the NVIDIA architecture. So as you know that it's from the thread, warp level, and the thread block level, and the grid level. So the layout system captures those hierarchy. And now we are using the linear layout, which is a function of the hardware location to the logical tensor index. So yeah, those the layout systems are, the most important part of the Triton. So here is the question. Can we use the layout for the CPU or even non-GPUs? So let's just start with the NVIDIA. So NVIDIA, so we have 32 threads per warp, and by default, 4 warps per thread block. And the thread, the CPU thread, not the CUDA thread, is more like a warp, right? So if Triton can generate code for warps, then the code maybe it's very similar to the CPU code. So I was trying to find a way, but so now I finally just realized. So what if we are setting just the 1 thread per warp, or just 1 warp per block? So then it might look like a CPU code, So I did a quick experimentation. So this is the NVIDIA backend. So here, I just changed the constant, just the one warp, and the one thread per warp, and the one thread block. So then, surprisingly, the NVIDIA backend already starts to generate a very CPU-like LLVM IR. Vectorization is also very important, right? But the Triton does already the vectorization for the load and store up to 128-bit or 4 elements or the 32 bytes. It is limited by some constants in the code, like a divisibility and the other some constants are there. So I was able to find it and increase them. So then, yeah, it was working pretty nicely. So here is a very quick comparison. So this is the very simple softmax example. Say that we have 1024 block size. This is the beauty of the Triton, right? So we are giving an illusion of the handling the block size, but the actual generated code is for the CUDA thread. So here, by default setting, each thread, each CUDA thread will handle 8 elements, right? So it's divided by 32 and the 4 warps. And then when it comes to load, so it is vectorizing up to 120-bit. And then when it comes to reduction, as you know that there is a multiple level reduction within the thread and within the warp and across the within the CTA using the shared memory. For CPU, so we can do like this one. So by setting just the one thread per warp and the one warp per block, entire block element goes to this statement. So this is actually what we do in Triton CPU. And then we were able to increase the vector size limit so that here the load and store does use the 1024 size of the vector length. And then when it comes to reduction, it just finished within the first level, just only reduction within the thread, no any, the warp, shuffle or something like that. So I did some, a couple of months ago, I did a quick experimentation. So I was able to pretty much of the unit test, less than 1,000 of the lines. So most of them are, it's really just a simple patches. For example, element wise, I need to promote to the type to the vector type. And the load and store, because the load and store for the NVIDIA, okay, so I implemented this idea on top of the NVIDIA backend. So the load and store, it uses a lot of the PTX. So I just changed it to the LLVM IR and the load and store, mask the load and store. It was working nicely. So the idea is there. So this is the benefit I am thinking. So I think the best thing is that we can share the knowledge and the experience across the Triton GPU and even for the non-GPU. It's not separate. Now we can just share everything together. And I was feeling, so for the future optimization, for the advanced optimization for the Triton CPU, so I think using the layout and the direct usage of the LLVM IR looks like a much more comfortable, and it looks like really like a GPU. So, for example, that operator, for me, it was a really straightforward than the vector dialect, the contract operand. So that's so one of my assessment. And also, another good point is that the many parts of the current Triton CPU are really portable. And this is another advanced topic I don't want to discuss today. The biggest challenges in the Triton CPU right now, so there is a very long compilation time because the block size is pretty big than the GPU. So I do believe, I think a layout can help kind of an automatic tiling to reduce the completion time because so we can also apply multiple threads, a warp concept in the CPU. I think this is fairly doable, but I haven't tried it, but it might be doable. I don't want to discuss today, but also maybe this, because we are showing the more of the Triton, the core of the Triton, maybe it might be easier for the upstreaming in the future. And that this is not my goal. And it's not about rewriting everything over the Triton CPU. It's more like the removing the vector dialectic dependency. That is right. So we require one-time effort, but maybe it will be paid off in the future. I don't want to oversharing and over refactoring. So yeah, the Triton is still the GPU first, which does not hurt any GPU path. And any GPU or the NVIDIA, AMD, or the CPU specific code will be kept in separately. I don't want to also change the terminology. And yeah, for example, the CUDA thread and the warp is kind of confusing for the CPU, but I think we can live with it. So yeah, so here is the summary of my idea. So I might propose the Triton Machine IR. So basically, it's sitting between the TTIR and the TTGIR. And it's really just a refactoring, and the TTMIR, mostly just the same TTGIR. It's only minus GPU-specific stuff, like a data operator or the shared memory. So yeah, it's just, at the end of the day, factoring. So here is the current architecture. So TTIR, the TTGIR, and this is the GPU space, and the CPU space. So this is the current rolling scheme. The new architecture, maybe with the Triton machine, TTMIR sitting between the TTGIR, and we can remove the vector dialectic dependencies. And yeah, so the TTMIR also can go to the LLVM IR, just like our TTGIR to LLVM. Okay, so here is the result of the quick prototype. I only spent like 2 weeks or 3 weeks, and basically it passes entire the unit test and test the core. There are some failures in the math library, and also I didn't implement the lower precision or the .3D implementation, but it's a fairly doable. And the code looks pretty decent. For example, the very simple vectorization, the vector load and store, the data operator looks fairly straightforward. The vectorization AVX512 were used. But there is some to do. So if you know that the LLVM on the Triton, there is lots of the unpack and the pack, right? So the intermediate data types for the Triton GPU, so we use just the LLVM struct. But it was not good for this idea because so we are handling many elements, like a 10K, 1K elements. So putting everything in the LLVM struct was crazy. So it was taking a lot of time for the compilation. So yeah, I was able to promote the vector type, but it didn't help actually. So I think we need to implement like a memref, or like a block pointer, then the LLVM struct. So yeah, that's one kind of a blocking issue right now. Another some issues is that so we need to fully implement some linear layout stuff, the data operator. Okay, so this is it. I just tried it, and it's very interestingly, the code of Triton actually can be repurposed, can be used for the CPU or even for the non-GPU. And I think it looks pretty interesting, and also Triton can be expanded broader. So if you are interested in this idea, so we can talk, and that the code is already there. So that's all I have. Any questions or the feedback? I will be happy to take it.
Go ahead, Thomas.
Okay, Thomas.
Yeah, a few questions. Very interesting presentation. So I'm curious a little bit of what you will get to reuse. Like, for instance, what would you do at this Triton Machine IR level?
Oh yeah, my proposal at this time, it's really for the reusing the layout system. So in the TTGIR, it's the TTIR really just the translation of the Python program. The TTGIR, so we are adding the encoding, the memory encoding, the layout stuff. And also there is lots of some lowering to the data operator, the shared memory stuff. But if you remove those GPU a specific stuff, the layout remains. And my idea was that the layout stuff can be pretty much reused by the CPU side. So it's more like the refactoring. The TTGIR at this time, it has lots of the CPU specific stuff, but I was able to remove pretty clean cut. Yeah, just.
What's left in the layout if you remove all the? That's the part I'm not understanding. Like, what's left of the layout if you're trying to not have anything GPU specific?
Oh, but it's still very interesting. So in a in this TTMIR, so you will have the layout for each tensor operation. So in the TTGIR, as you know,
I missed the word. Could you repeat the sentence?
Yeah, in the TTGIR, so every tensor operations layout are attached, right? Like a block or the MMM or the sliced encoding. So that's all we need for the TTMIR. So when you look at the make TTGIR at the very first time, so we are converting to the TTGIR. That time we are attaching the memory layout, then followed by other convert some shared memory, something, data operator. So I'm just taking out of the just separate those two steps. It's a fairly straightforward. So TTMIR, it's really just TTIR plus the layout stuff. So that it turned out this part can be really reusable by the CPU or even for the non-GPU.
Okay, yeah, I guess I'm not able to understand what that would look like, but maybe I would have to look at some examples.
When you look at the code, it's actually fairly straightforward. I just very clean cut in the TTGIR level.
Yeah, maybe looking at IR would help. So but I mean, overall,
do you have examples to share, Minjang? Samples.
Oh yeah, it's really just a TTGIR. Oh, okay. So let's just see. Let me show. Let's just see. Oh, for example, in the vector addition, it's just the same with the TTGIR, exactly the same. And then when it comes to really the same, because when it comes to simple vector addition, there is no any dot operation, the shared memory stuff. When it comes to matrix or the tensor operations, so we don't just promote to the shared memory. So it just load and store with the attached the layout stuff. So yeah, I can share. I can put in the example in the slide, but I don't have it right now. But it's really just the TTIR minus GPU specific stuff. I can show it.
Yes, the shared memory and stuff. It's coming fairly late in TTGIR, but even I guess what I'm trying to say is it feels like the reuse overall doesn't seem to be super big in the sense that I don't like a lot of the passes that just don't apply on CPU, right? Like the coalescing pass, it won't apply. Like a lot of the passes they won't apply. Some of the passes they will apply. That's the ones that are agnostic to what's in the layout. Like for instance, the layout propagation pass. Sure, it makes sense to reuse it. But then it feels like it's just a matter of having a new set of layouts for CPU, and then you get to reuse this thing without really needing an extra layer or anything like that.
So you're right. So for the CPU, all we need is just a block layout, the slice the layout, and the data player layout. We only need the 3-1. And then when it comes to, of course, we don't need the coalesce or whatever something, but there is split or the reduction of scan or the data player, the basic stuff were actually working for the CPU because they are just working for the layout. And I'm just fixing the layout to just the one thread per warp. Actually, it was pretty surprising. It was working actually. Yeah, you're right. So there are many GPU stuff, but the pretty decent. Basically many of the Triton GPU to LLVM stuff were actually mostly for the CPU as well. So yeah, that's the what I have found. Yeah, it was pretty interesting. Yeah. Yeah, even for me, I was surprised. It was just working. Yeah.
But which ones? I mean, I guess you have like element-wise shows they're very trivial, like maybe load and stuff, but like things like reductions won't work, right? The MMA, like the dot operations won't work. I feel like
it was for the reductions. Though I was able to stop at the very first time. In the reduction in our GPU code, there is a 3 steps. The reduction within the thread. So I only just used that part. That was working for the CPU. And and also the data operator is similar. So I don't need any MMM, right? It just goes fall back to the very simple FMA. It was working for the CPU, yeah, because so yeah, it turned out pretty general, yeah.
Okay.
So Minjang, what is the next step? Are you going to continue developing this, or do you want to upstream this? Or what is the next step in your mind?
This is just the idea. I just scratched, just a short amount of time. The code is there. It's a little bit stale right now, about 2 months old. But yeah, everybody, if just like another idea, like try to share the idea. So yeah, I might be working to based on the whatever latest one. So I want to make also the separate fork. So yeah, if you are interested in a kind of new idea of the, like try to share the idea, so you can try it. But yeah, I will do some, test off. But right now, I don't have a big plan to work on right now until we have a bigger motivation. But I want to share this idea. Triton can be used for other purposes.
Sure. Please include the repo details in your slides so that we can put it up.
Yep, I can show the Yep.
Thanks. Okay. Thanks, Mingjang. Next is Janhui, I think. Yeah, I see you. Yeah, so Janhui is going to give an update from Intel about the Tensor descriptor API. Yeah, go ahead.
Sure. Can you see my slides?
Yes, we can see them. Yeah.
Okay. Yeah. So so mine is relatively short. I only have 2 slides, but the first slide is on a simple update on this Tensor descriptor API, how it can map to Intel GPU. So then I have one more slide about more for discussion, like what is Triton's plan. So first of all, like recently, we saw this Tensor descriptor API was introduced, and there are 2 important PRs. The first one basically have this Tensor descriptor API, and then recently also added the Tensor descriptor data type. And this is the example we can extract from the PR. It's from a unit test. We feel maybe it's not the final official code example, but it tells us a lot. So overall, we really like it. It is a generic tensor description for the global memory, some tensor in the global memory, and also including how it will be blocked when the hardware block loaded. And they get rid of the needs for user to prepare a target specific tensor either on the host side or the device side. So there's no such target specific thing. And actually, previously there's a version make a TMA tensor descriptor, which is like there's a bunch of target specific things. Here the pointer sent through this kernel is just a pointer to the the matrix, the tensor buffer, and there's no like a target specific like a pointer here. Previously there is a TMA descriptor pointer. So overall, we like this one a lot. So underneath, when we map to XeGPU, our currently we map into a like intrinsic function. That function actually does not require this tensor descriptor to be saved in any global memory and pass the global memory pointer and things like that. So it just pass all this information, and underneath we also pass this global memory block shape and also this offset together, all together to this. There's a one load block load instruction. We just pass them all. So one thing particularly we believe this is still experimental, because we still see, for example, there's experimental here, and also this is a little bit puzzling, is that it is not the traditional Triton language style like TL.load. Instead, it's just using, maybe it's something intermediate. We believe in the future it probably should be TL.load with the tensor descriptor and then with the offsets. Yeah, but overall we are very excited to see the Triton evolving to this more generic form, and we look forward to see this pushing to be more official. Yeah, with that, I think we want to go to the next page. Just want to have some high-level idea how like this tensor descriptor will be eventually be positioned, like whether we want to make it an official one. So like how we deprecate the TM descriptor, and then how we deprecate the block pointer. Whether we want to, the other thing is that how we deal with this like a block pointer. Should this block pointer being removed completely? One observation we see is that this block pointer actually has a lot of similarity with this tensor descriptor. Yeah, so that's one question, is how Triton will treat this block pointer, whether just to get rid of it, or is eventually this tensor descriptor will evolve to be something like a block pointer. And
yeah,
then
so
yeah,
I think I can answer some of these questions. So the current plan is just to take what we've got currently. Currently, it doesn't quite work properly with the pipeliner if you're creating new descriptors inside of a mapmul loop. So there's like some small technical things that need to be fixed, and then we'll try using it internally and see if we like this API, see if it's good, and then eventually make it non-experimental. So the plan is that it will, if all things go well, look more or less like it does today. Block pointers, yeah, they're kind of hopeless at the moment. So we're planning to eventually, once we can completely replace all the block pointers with this tensor descriptor API, just get rid of them and deprecate it. And yeah, obviously we're going to update the tutorials, but it's not really in a state where we want to publicly advertise it yet. But it is in a very similar state to how we think it should be in the end. So if you start basing some of your work on it, I think that's probably fine. Also, in regards to like calling TL.load, I think that was maybe a bit of a mistake of the block pointer API, that it kind of looks as if you're just doing a normal load, but actually it's a very special thing with all these extra alignment requirements and things that would either behave nothing like a normal TL.load, or kind of fall back and have bad performance. So we're very specifically trying to have an API that's separate and is like well documented in what are the exact requirements to get good performance with this descriptor object, and this is doing a separate thing that you need to program differently. Does that make sense?
so you're saying this, go ahead.
Now, if you go back to the previous slide, generally, so here you have, so if you had tensor descriptor, then would you also have a descriptor.store? operation is that this is not shown because the output pointer is not a block pointer or a tensor descriptor.
Yeah. So this is just a test that, like, if load and store were broken in the same way, the test would pass. So I'm intentionally mixing both types just for the test, but there is an equivalent store operation.
Okay, so I didn't quite. So the TL.load operation could be given a tensor descriptor and the offset, but you're saying that you rather implement a new operation to totally disambiguate that operation with the other one. Okay, I guess that's what you're saying. That you won't be able to use the TT load, and it's going to be staying as descriptor.load at this point.
Yeah, exactly.
Yes, it reads to me is as if it's like a different dialect. You have the dialect. This is a name, prefix for dialect name.
This is not a dialect name, right? We have already other cases where we have member function on like tensors, right? This is not. It's not the first time we have this kind of this kind of like syntax, right?
In fact, I'm pretty sure you can do tensor.load.
Okay, so it's more like a
I don't know about
Triton
load
class.
I guess I'm more curious about what would be the Triton IR for it. There will be a new operation, or yeah, it's true. Like we're talking about the Python level, but at the Triton IR level, that descriptor.load will become a TT.load, or it will become some other operation.
Yeah, so currently it's called experimental descriptor load. But obviously, once we take out experimental, we'll remove the experimental part. I think that was a bit of a mistake with the block pointer API, that it's the same operation, so it makes writing the actual passes a bit more confusing, because you have some operands that either exist or don't exist depending on whether it's a block pointer or a normal pointer. So just get away from that. And
it was just curious, but thanks for clarifying.
Yeah, I do also hear people ask a question. You said block pointer is hopeless, but if we compare these two things, right, like this block pointer is just the tensor descriptor with an offset. Maybe there's also an order. So what's wrong? We just kind of also like make this tensor descriptor include this block offset, and then it's what's really wrong with this block pointer programming model. It appears to me like if you have this offset as initial offset, then you advance, you always use advance. It's just tell you more cleanly what are this like block is moving.
Yeah, so for one, it's a bit awkward to deal with having these different pointers everywhere, where you're like, particularly in the pipeliner, when we're updating the descriptor, we have a single descriptor that flows through multiple loop iterations and is long lasting, and it just makes it easier to analyze in the IR. But the bigger thing really about making it a completely separate API is just that before, block pointer was trying to accept any kind of generic load, but if you did it right, it would pattern match to the efficient load instructions and magically be a lot faster, but in a kind of opaque way. Whereas this one is going to explicitly assume all of the alignment requirements and give you the fast instruction always, and fail if you don't have the correct alignment.
Okay. So the more narrow semantic, and user need to be aware of this when they use it. It's like just use it as a high-speed optimization path if you choose to use this one.
If you had to speculate, what would be the timeline for the tensor descriptor to become official? We're talking about like a month, 2 months, more than that, 6 months. Doesn't have to be, just if you have an idea.
Probably in the sort of range of a few months. I don't know if I could get more specific than that.
Okay.
Have you considered using like a strict mode for block pointer rather than, you know, this new tensor descriptor? If the semantics are, you know, just a more scoped down, you know, version.
Yeah, so I mean that's would certainly work, but part of it is just trying to clean up some of the technical debt and just take a clean slate sort of thing. Does that make sense? I mean, I know that
It makes sense, but now we have, you know, two sets of operators that do very similar things.
Yeah, the plan is definitely to deprecate block pointer and transition over though. So long term, we're going to just rip all the block pointer stuff out.
And do you also deprecate the TMA descriptor?
Yeah, so it's not currently clear if we can support that in the general case. So it's not going to be well supported at the moment, and the preferred method for accessing TMAs is going to be the Tensor Descriptor API. We might just leave the experimental support as it is because I think some of the meta work depends on it, but long term, it's not clear what the story is going to be there. If we can, it might be nice to have a host-side descriptor creation API that could be cross-platform, but yeah, there's no clear decision there yet.
I think it's generally good to have one unified API to describe tensor descriptor. Because like usually now when people write a Triton kernel, they use the tensor pointer, which is lower level, and we attempt to raise it before and find there's like a number of reasons that cannot be safely raised back to tensor, that block pointer level. And so if we want to deprecate block pointer and use tensor descriptor, that means, as you say, it's more restrictive, and that means there's some pointers cannot be described with tensor descriptor, and so it will be forced to use the tensor pointer, which I think it's opposite of what the MLIR, the progressive lowering idea is. So if we can have something generally more high level and depends on the cases, we may or may not be lower to tensor pointer will be more ideal. What do you think?
Well, we're just trying to avoid some of these kind of opaque cases where there's some magic in the compiler that if certain conditions are met and it's able to infer these, then things magically get faster. It's like, I guess maybe there's a path where there's a like loose version of the tensor descriptor API that does allow more general pointers and is, you know, expected to be slow. I guess there's nothing inherently wrong with that. It's just not the focus at the moment.
Mm-hmm. Do you worry is that a concern if like newer hardware comes and the restriction or requirement become different, and then this API that is very specific for certain assumption will become different and we need to change it?
Yeah, I think that's an obvious problem, but certainly for the near future NVIDIA hardware, I think we're fine. And yeah, it's hard to strike the balance between being expressive enough to get good performance versus being so general that it can support all hardware possible. Yeah, this is just one point in the design space. I don't know that I can really say much more. It worked well for our use case, and if there's any major problems with it, we're open to discussion, I guess. Tamar, do you have any thoughts?
No, I agree with you. I mean, definitely it's very a lot of trade-offs, and you cannot predict the future. We do think so far that the Tensor descriptor maps much better to most existing hardware, and that the block pointer is the advanced and the older parameter was it just did not fit enough like any of the existing hardware, and just makes it harder for the compiler for no good reasons.
Great, sounds cool.
Okay, thanks, Jianhui. Are there any other questions or comments?
Yeah, just hope this one make it official earlier, so we converged to one thing.
Okay, so if there's nothing else, then we can close for today. Thank you, everyone.
Thank you. Bye-bye.
Thank you.